Towering skyscrapers define the skylines of the world's greatest cities, proud symbols of mankind's prosperity. Essential to any building are the elevators that move people up and down quickly and safely. New York City got its first electric lift in 1889. Tokyo got its own 1 year later. Japan's elevator industry surged during the construction boom of the 1960s. Skyscrapers were a new phenomenon in the country, and they prompted elevator manufacturers to enter the global race for faster and more efficient systems. Technology rapidly evolved, and soon Japanese elevators were breaking speed records one after another. This year, the current world record is about to be broken. The 632-meter-tall Shanghai Tower is nearing completion. Its elevators are designed to reach speeds of up to 1,080 meters per minute, or 64.8 kilometers per hour. Visitors will be whisked from the second basement to the 119th floor in just 55 seconds. The company behind this project is Mitsubishi Electric, one of Japan's top elevator manufacturers. Engineers at the company rely on a testing tower to develop the world's most advanced lift systems. Day in and day out, they test the limits of their devices to ensure top performance and safety. Elevators are essentially simple devices. A cabin and a counterweight are connected by a rope. A winch raises or lowers the cabin along vertical rails. The higher the speed of an elevator cabin, the greater the shaking and the noise, problems that engineers must address. Achieving ever greater speeds demands ingenuity. And staying ahead is what drives the industry. Fast and smooth, today's elevators are ubiquitous and get us where we need to go. And they allow us to see our world in thrilling new ways. In this episode of JTech, we'll take you to the top of the world in record time. Hi and welcome to the program. I'm Marc Carpentier. The invention of the modern elevator is attributed to the Greek mathematician and inventor Archimedes about 2,000 years ago. His device was simple but effective. It consisted of a platform, a pulley, a rope, and a lot of elbow grease. The first machine-powered lift was invented in Britain in 1835 at the height of the Industrial Revolution. It was steam-powered. The next step in elevator technology came in the 1930s, when the world's first skyscrapers were built. Elevators got faster and more efficient, and to this day, the technology has never ceased to evolve. Today's modern lifts are reaching ever higher, so much so that we can wonder if the sky really is the limit. In 1931, the elevators in the Empire State Building in New York were the first to breach the barrier of 300 meters per minute. They took visitors to the top floor at a speed of 360 meters per minute. That's about 22 kilometers an hour. In 1973, the elevators at the Sears Tower in Chicago could reach a speed of 540 meters per minute, or a little more than 32 kilometers per hour. 5 years later, in 1978, a Japanese-made elevator set a new world record at the Sunshine 60 building in Tokyo. Its top speed was 600 meters per minute, or 36 kilometers per hour. Japanese manufacturers kept pushing the limit, and in 1993, they set a new record of 750 meters per minute, or 45 kilometers per hour, at the Yokohama Landmark Tower. The current record belongs to Toshiba, whose elevators take you to the top of the Taipei 101 building in Taiwan at a dizzying 1,010 meters per minute, or 60 kilometers per hour. And that record too is about to be surpassed by Mitsubishi Electric. Their elevators will be the world's fastest when the 632-meter Shanghai Tower in China opens in 2015. They'll reach a speed of 1,080 meters per minute, or almost 65 kilometers per hour. Elevators have come a long way in only 80 years, and they'll only get faster. Already, an elevator being developed by Hitachi will approach the speed of 70 kilometers per hour. That's nearly 1,200 meters per minute. Several units will be installed at the CTF Finance Center in Guangzhou, China. The 530-meter tall skyscraper is scheduled for completion in 2016. Fast elevators are impressive, but speed isn't everything. Japanese elevators have a reputation for being particularly silent and very smooth. We're trying a little experiment here at the landmark tower in Yokohama. We set a coin on its side and we take a ride 69 floors up. Remember, the elevators here reach 750 meters per minute. Now that's pretty convincing. A smooth and comfortable ride is essential for passengers to feel at ease in an elevator. Nobody likes a shaky cabin when it's dangling hundreds of meters in the air. Many of us already get claustrophobic being locked into a confined space, and any shakiness that's going on is going to heighten the fear that something could go wrong, like what if the cable snaps and the cabin plunges to the ground? Well, elevator manufacturers knew early on that if they were going to get people to ride on their devices, they had to alleviate any concerns for safety. Elisha Graves Otis in 1852 was the first to invent a safety device that prevents elevators from falling if the ropes happen to fail. This was the defining moment that accelerated the development of elevators. In 1889, Elisha Otis founded the Otis Elevator Company and produced the world's first electrically operated elevator in New York. The following year, a Japanese company followed suit. Its elevators, installed in the 30-meter tall Ryounkaku building in Asakusa, could reach the 8th floor in 2 minutes, on par with what Otis had achieved. Then came World War II, and elevator development in Japan grinded to a halt. Lifts were deemed as unnecessary luxuries and banned. The metal used to make elevators was diverted to the war effort. When the war ended, Japan was lagging far behind in elevator technology. And when the country's first skyscraper was built in the 1960s, it was Otis that got the contract for the building's elevators. This marked a big setback for Mitsubishi Electric. It took 10 more years before Mitsubishi could once again compete with its American rival. Let's take a look at how the company's engineers tackled this race to the top. After Japan's defeat in World War II, U.S.-led Allied forces occupied the country. They set up their headquarters, requisitioned burnt-out buildings, and turned them into barracks. That's when Mitsubishi Electric got back into business by repairing the building's elevators. The company resumed full-fledged production of elevators in 1949. Akira Miyagi was named head of development. As an electrical engineer during the war, he had developed instruments for military aircraft.
I was extremely grateful for this worthy project. I was motivated and gave it my very best.
Japan's post-war reconstruction boosted demand for more advanced elevators. Mitsubishi Electric produced many large, high-end systems for hotels and department stores. In December 1961, Miyagi heard about a super-fast model that was being installed in the United States. The elevators in New York's Pan Am Building could climb all the way to the 59th floor at a maximum speed of 510 meters per minute. The elevators there were 3 times faster than Mitsubishi's. Eager to try them out, Miyagi jumped on a plane to the U.S. But he wasn't impressed. The ride was uncomfortable. The cabins were prone to violent shaking, and they were very noisy. Miyagi realized that to compete at the international level, he'd have to come up with better technology. His elevators would have to be faster and more comfortable than those in the U.S.
They had to move fast and efficiently. One way or another, I was going to build the world's best elevators.
Until then, Japanese regulations had limited the maximum height of buildings to 31 meters, or about 9 stories. In the 1960s, the country's fast economic and demographic growth called for the construction of higher structures. Regulations were amended in 1964. Japan was finally able to build its own skyscrapers. This led to a construction boom. The first high-rise project was the Kasumi Gaseki Building. At 147 meters and with 36 floors, it was Japan's first skyscraper. Miyagi and his team immediately saw the project as a unique opportunity to showcase their engineering know-how, but they lost the contract to another company. Toyo Otis was the Japanese subsidiary of the Otis Elevator Company, the world's first manufacturer of elevators. Otis's impressive track record in the U.S. and the reliability of its technology gave it the edge over Mitsubishi. The completion of the Kasumi Gaseki Building in 1968 marked the arrival of the first super-fast elevators in Japan. They could reach a speed of 300 meters per minute and carry more than 10 people to the top in just 30 seconds. Tokyoites now had a new vantage point from which they could admire their fast-growing city. Mitsubishi Electric was given a chance to redeem itself in 1971 with the Keio Plaza Hotel project. It built a system capable of 360 meters per minute. The company was closing in on the world's fastest elevators, still being manufactured by Otis. The record-breaking opportunity came 5 years later. In 1976, Mitsubishi Electric was awarded the contract to build the elevators for the Sunshine 60 building. At 240 meters, it was the tallest building in East Asia. Miyagi was close to retirement then, so he handed over the project to one of his junior colleagues. Akira Takamura was a mid-level engineer. He was determined to break the world record of 540 meters per minute set by Otis. He aimed for 600.
I told my boss, just let us handle the project. I said we had to have the contract, even if it wasn't profitable.
Mitsubishi Electric's management was opposed to the idea. The budget would only allow for a system capable of 540 meters per minute instead of 600. But Takamura refused to back down.
The fact of the matter was, achieving a new speed record would put us at the forefront of elevator technology.
Takamura's enthusiasm won over company executives. and in April 1973, he was appointed to lead a team of 100 engineers with the aim of breaking the world record. The 60-story office tower was designed to house 8 elevators. Takamura's mission was to make 2 of them the fastest in the world. He first had to re-engineer the hoisting mechanism. The elevator had to be able to carry 24 people up to the 60th floor at 600 meters per minute. This called for a motor more powerful than anything Mitsubishi had ever built. The company's know-how allowed its engineers to develop the world's first 100 horsepower elevator drive. The 8.7-ton, 1.7-meter tall beast was 3 times larger than previous models. Now that Takamura had the power he needed, he had to find a way of controlling it.
It's extremely difficult to control an elevator's acceleration and deceleration. We needed to make the hoisting mechanism pull the cabin in a way that it wouldn't be uncomfortable for passengers.
An elevator's cabin is carried up and down by an array of cables called ropes. At the moment the motor is activated, it creates a sudden jerk on the ropes and makes them wobble. This shaking is transferred to the cabin. To keep this from happening, the acceleration must be controlled until the motor reaches maximum speed or decelerates until it reaches a full stop. Engineering a system to control acceleration was a daunting task. But Takamura knew where to start. He relied on his experience during the days under head engineer Miyagi. Flashback to the 1950s. Mitsubishi Electric has just started making elevators again. The company has received a complaint from a customer. The customer says riding the elevator makes him feel ill, as if his stomach was in his throat. Executives immediately set up a team to investigate the complaint. Takamura is invited to join under the leadership of Miyagi. The company's orders are simple: identify the cause and find a solution. Takamura heads for the test tower. He installs a speedometer on the cabin and invites his colleagues to take a ride. Over the next several months, he carries out test after test, subjecting his colleagues to different combinations of speed and acceleration, until he's able to identify an ideal curve that doesn't cause discomfort. Takamura decided to apply the same curve to the Sunshine 60 building. It meant accelerating the cabin for 12 seconds up to the maximum speed of 600 meters per minute, and decelerating it over the same amount of time until it reached a full stop. The next step was to develop a speed control mechanism capable of replicating this ideal curve. The device that controls a motor's speed is called a line reactor. Engineers mounted them on the Sunshine 60 building's elevator motors. At the time, computers were still in their early stages, so acceleration and deceleration of the motors depended on mechanically adjusting the amount of electric current running through the reactors. A reactor works by running a metal rod through a series of coils. Changing the depth of the rod through the coils controls the amount of electric current running through the motor. The system needed to be extremely precise. A 1 millimeter discrepancy in the depth of the rod would result in the cabin undershooting or overshooting the target floor by as much as 12 centimeters. In order to attain the ideal acceleration and speed, engineers manually adjusted the reactors for the Sunshine 60's elevators. April 1978. The building was completed. The next challenge the engineers faced led them into uncharted territory. They needed to learn how to control the shaking of the cabin. This was crucial if they were to build the world's fastest elevator.
It turned out the shaking was mainly caused by wind. We only found out about this problem after the building was completed. We were unable to detect it before.
The Sunshine 60's 240-meter structure was vulnerable to strong winds, which caused it to sway considerably. This made the ropes oscillate, which in turn shook the cabin violently. Takamura and his team had to find a solution to keep the elevator stable, even if the building swayed.
When this problem emerged, we realized we had to find a way of absorbing that oscillation. So we all got working on it.
Takamura's team tried using a damping device widely known in the automotive industry: shock absorbers. His team installed a suspension system with dampers between the cabin and the ropes. This helped to absorb lateral swaying of the cabin. At the time of its inauguration, Sunshine 60 boasted the world's fastest elevators, with a speed of 600 meters per minute. Each day, they carried 9,000 eager visitors to the 60th floor observation deck. People praised the comfortable ride.
I had plenty of engineering friends from abroad, and one I was particularly close to used the English word polite. I thought, this man really gets it. In a way, the elevator behaved in a considerate way from start to finish. It was silent and, well, polite was the perfect way of describing it.
The reputation of these polite elevators reached overseas, and soon the experience of boarding a Mitsubishi elevator came to be known as the Japanese ride. Now that Mitsubishi Electric had figured out a way to make their elevator rides smooth as silk, the race was on to develop technology that could perform in ever taller buildings. The 1980s saw an unprecedented rush to build skyscrapers. This spurred demand for faster elevator systems capable of ferrying people and goods efficiently. But tall buildings posed a challenge to engineers to maintain the stability of the cabins. This was crucial if elevators were going to go faster and higher. Japanese manufacturers were determined to stay on top, and they aimed at establishing new world records for elevator speed. And they succeeded. In the 1990s, Japan became the world's largest producer of elevators, with Mitsubishi Electric leading the way. The landmark tower in the port city of Yokohama is a 30-minute train ride south of Tokyo. It was completed in 1993. On the lower floors are shops, restaurants, and clinics. Above are offices and a hotel. On the 69th floor is the observation deck. The landmark tower has Japan's fastest elevators, and they were once the world's fastest. They carry visitors to the observation deck 296 meters above ground at 750 meters per minute, or 42 kilometers per hour. The ride takes only 40 seconds. When these lifts were being developed, engineers were aiming to establish a new world record. Their original plan was to reach 700 meters per minute, improving on the Sunshine 60's 600 meters per minute. However, workers on the project heard about another system being developed in the US that would reach 723 meters per minute. Japan had become a major exporter of elevators, and Mitsubishi Electric was determined to hold on to its title as the maker of the world's fastest. If engineers were to achieve that goal, they needed to improve on the technology, and that meant redesigning every component. Mitsubishi Electric began by developing a new winch. It would be the largest in the world. This device is huge, measuring 2 meters in height and weighing 12.5 tons. Compared to the Sunshine 60's winch, it has 5 times the power output and is 20% faster, running at 240 revolutions per minute. The winch lifts 10 cables of 1.8 centimeters in diameter. The elevator cabin itself weighs 1.6 tons and carries up to 24 people. Engineers at Mitsubishi were able to develop an extremely powerful motor. But as with the Sunshine 60 project, the landmark tower had problems with cabin instability. The system had to cope with 2 different types of movement. First, there was building sway. The landmark tower sits by the bay. Strong onshore winds can cause the entire building to sway considerably. Then there was vibration caused by uneven rail joints. Though small, this vibration would be magnified at high speed. To solve these problems, the engineers developed stronger rails. The density of the steel used to make the rails was increased by 25%, improving their rigidity. The rails were assembled at night, when the wind is low, to maximize precision. Skilled technicians joined more than 700 rail sections one at a time. Despite these efforts, it was impossible to completely resolve the vibration problem. Even the smallest misalignment in a joint would produce noticeable vibrations at 42 kilometers per hour. Engineers had to improve the roller guides, the wheel sets that hugged the rails on either side of the cabin. Roller guides are designed to ensure smooth vertical movement of the cabin along the rails. But if the rails are even just slightly warped, or if the joints are slightly misaligned, the cabin will shake. Previous elevator designs had spring mechanisms attached to the roller guides in order to minimize lateral movement. But it took considerable force for them to function, so they were unable to absorb the smaller vibrations caused by uneven rail joints and other factors. And that's why Mitsubishi Electric chose hydraulic dampers, similar to those used in the automotive industry. Engineers believed these dampers would absorb all kinds of vibrations, big and small, much more efficiently. The hydraulic dampers were fitted to the roller guides and proved effective. They simultaneously removed the effect of major lateral movements caused by the swaying of the building and minor vibrations generated by the rail joints. These innovations reduced shaking of the cabin by 20% compared to other high-speed elevators. We've come to the 30th floor of the landmark tower, roughly halfway up the building. We'll get a chance to see the neighboring elevator cabin as it travels down the shaft. The cabin will start accelerating as it leaves the top floor and will reach its top speed right around this point. We'll be able to see it go by through the emergency evacuation hatch that engineers have kindly opened for us. Oh my goodness. Did you see that go by? If you blinked, you didn't. That was really fast. Not only that, but it's very, very smooth. I was expecting a lot more rattling and shaking going on, but not at all. Very impressive. These elevators are notable not only for their speed and smoothness, but also for how quiet they are. Their low noise level is mainly the result of the cabin's shape. The cabins were cleverly designed to be aerodynamic. Their streamlined shape minimizes the effects of air resistance as they move through the shaft. Their shape was borrowed from the bullet train. In contrast to the angular appearance of ordinary trains, the Shinkansen has a streamlined profile to reduce drag. The top and bottom sides of the Landmark Tower's elevator cabins are fitted with profiled covers that help them slice through the air more efficiently. In addition, engineers worked at reducing the noise generated by the cabin's outer walls. They built an insulated double wall structure to prevent vibrations from the outer walls from reaching the occupants inside. Thin steel plates were inserted in between the walls to help dampen the sound, bringing the noise level inside the cabin down to just 52 decibels, barely louder than the hum of a refrigerator. The Yokohama Landmark Tower elevators are quiet, fast, and smooth. Let's replay the coin test. We're now going to demonstrate just how smooth this ride really is. We stand a 10-yen coin on its side on the cabin floor and take a ride from the second floor all the way to the top. And just in case you're wondering, this test is for real. The elevator makes a smooth start, but will the coin stay standing all the way to the 69th floor? Now that's pretty convincing.
How was the ride? Was it smooth, comfortable?
Yeah, it's smooth and comfortable, and it's great.
And how was the impression of riding on the elevator?
It was really fast. I feel like I'm riding a comfortable sedan.
20 years on, the elevators at the Yokohama Landmark Tower are still going strong. They ferry an average of 1,500 visitors every day who, on their way to the stunning view at the top, experience a fast and comfortable Japanese ride. About 1 decade after the inauguration of the Yokohama Landmark Tower, the record for the world's fastest elevator was broken yet again. Toshiba's system for the Taipei 101 building in Taiwan broke through the 1,000 meter per minute barrier. These elevators take passengers up to the top at 1,010 meters per minute, or a little more than 60 kilometers per hour. Japan's three major lift manufacturers, Mitsubishi Electric, Toshiba, and Hitachi, are constantly competing to outperform each other. This year, Mitsubishi is seeking to set a new world record for the third time. And it's not surprising that it'll take place in a city where skyscrapers are mushrooming, like in few other places in the world, Shanghai. China has in fact become the world's leading consumer of elevators. 500,000 units are installed in the country every year. That's 60% of global output. And it's putting pressure on Japanese companies to keep improving their technologies to stay on top in that market. Mitsubishi Electric's latest project is the Shanghai Tower. The 128-story, 632-meter structure has already become a proud landmark of this bustling city. The exterior is now complete, and workers are racing to finish the interior, including the elevator system, by the end of May. The super-fast elevators will reach a record speed of 1,080 meters per minute. That's 64.8 kilometers per hour. This marvel of engineering is the result of several years of research and development. The main components of the system are the massive winches. Since 2004, Mitsubishi Electric has been using permanent magnet motors for models that climb 300 meters per minute or more. I believe it's called a PM motor, a permanent magnet motor. Can you tell us how it works?
Yes, this is a PM motor, or a permanent magnet motor. This winch system is made up of three main parts. The PM motor itself, a wheel called a sheave that holds the rope, and a braking device to hold the cabin when it stops. The most important part is the PM motor. It has an internal wheel fitted with alternating magnets of opposite poles. Surrounding the magnet wheel is a series of coils that create three different phases of magnetic force. These coils suppress torque ripple and make the inner wheel turn very smoothly.
A PM motor relies on magnets with a permanent magnetic field. Wire coils serve as non-permanent magnets that create a magnetic field only when an electrical current passes through them. When the coils are electrically charged, they become electromagnetic and are repelled by the permanent magnets. It's this force of repulsion that causes the motor to rotate. An engineer at Mitsubishi Electric's factory showed us a prototype of the motors that are being installed in the Shanghai Tower.
The winch is over here.
This is Mitsubishi's newly developed PM motor. It's almost 2 meters tall and is 100 times more powerful than a standard 6-person elevator. That's how much muscle it will take to set a new world record.
The motor is mounted behind the winch. This part in front is a disc brake. The middle is the winch, we call the CV. It houses the pulley that carries the ropes. It's a bit hard to see, but if you look over here, you can see the ropes.
What is so special about this particular motor?
It reaches a speed of 65 kilometers per hour. To achieve that, it relies on what is called a double three-phase motor. It's actually two motors that are mounted together and synchronized. Now, we're going to turn on the winch.
No, that is at full speed. I'm amazed at how quiet and smooth that is. I was expecting it to be a lot louder for some reason.
Thank you. That's right. We built it in a way that allows it to run quietly without transmitting any vibrations to the passengers.
It won't be long before visitors at the Shanghai Tower can appreciate the true smoothness of the world's fastest elevators. Another crucial element of the elevator system is the rope array. The steel cables have been reinforced. They are engineered to support not only the weight of a cabin and passengers, but their own weight over a length of more than 600 meters. That's a lot of rope and a lot of weight. 10 tons. Conventional ropes are made from linen fiber and twisted steel wire. Lifting a 10-ton weight up 600 meters at high speed could cause too much friction between the steel wires and lead them to break. The wires in the improved ropes are wrapped in a special resin, which reduces the heat caused by friction. To further reinforce them, the diameter of each strand was raised from 18 to 20 millimeters. Resistance tests have shown these ropes can sustain a weight of 300 tons, the equivalent of a long-haul passenger jet. Engineers will be using an array of 10 ropes for each cabin of the Shanghai Tower's elevators. Mitsubishi Electric now had a winch and cables that can propel an elevator cabin at a world record speed. But that isn't enough to win over the passengers. A fast ride is thrilling, but a fast, shaky ride is terrifying. Engineers had to ensure there would be no discomfort to passengers if they were going to preserve the reputation of the Japanese ride. In the case of the Shanghai Tower, engineers were confronted with a type of vibration they hadn't encountered before. At slower speeds, the vibration from the rails led the cabin's outer and inner frames to shake in the same direction. Adding dampers to the roller guides on the cabin's outer frame had solved that problem. But at a speed beyond 1,000 meters per minute, the inner and outer frames would shake in opposite directions. The engineer's answer to that was active roller guide technology. They attached sensors to the inner and outer frames and inside the cabin. These sensors measure vibrations several thousand times per second. They send the information to computer-controlled actuators connected to the roller guides. The actuators then apply pressure in the direction opposite to the vibrations and cancel them out. On an active roller guide, there are actuators on each of the 3 wheels. The actuators are made of permanent magnets and coils. The magnets are attached to the coils and create a magnetic field. The coils exert a force against the axle of the wheel. Here's a demonstration prototype of the active roller guides. The active roller guides are turned off. The shaking is as clear to see as the water in the glass. When the roller guides are activated, they instantly cancel out the swaying, and the water goes still. The system also helps to eliminate the effects of disturbance created when 2 cabins run past each other. The last problem Mitsubishi's engineers had to tackle was noise. They had already adapted the shape of the cabins to match the speed requirements at the Sunshine 60 and the Landmark Tower projects. They knew that the faster speeds in the Shanghai Tower would produce even more noise. Satoru Kato was in charge of fixing this problem.
In Shanghai, if we use the same cabin design as at the landmark tower in Yokohama, we expect that the noise level inside the cabin would rise by about 10 decibels.
Kato's response was to further elongate the cabin. The improved aerodynamic profile diminished air friction, thereby reducing noise. With the equipment tested and being installed at the Shanghai Tower, Mitsubishi Electric's engineers are now anxious to see their elevators in action.
We're both worried and excited at the same time. When we talk about discomfort and noise, we're not just talking about making our elevators silent and stable. We're focused on constantly improving our technology and developing elevators that provide a superior riding experience.
It won't be long now before Mitsubishi Electric's engineers know whether their new elevators live up to everyone's expectations and set a world record for a third time. Japan's advanced technologies have produced the fastest and most comfortable elevator rides in the world. But engineers have other surprises in store for us. Smart elevators are already being developed with systems that recognize each cabin passenger and take them where they want to go without having to push any buttons. In its quest to build the world's best elevators, Mitsubishi Electric is thinking beyond passenger comfort. It's now trying to minimize the time we spend waiting for an elevator. Standing in the crowded hall of an office tower is not the best way of starting your day. Engineers have a few ideas about how to solve that nagging problem. Elevator systems at Mitsubishi Electric's headquarters in Tokyo are equipped with artificial intelligence. Employees simply flash their badge at the front gate. The system immediately knows where they're going and directs them to a specific elevator. Computers predict the elevator's locations several minutes ahead of time and are able to manage the flow of passengers and minimize waiting time. When the passengers board a cabin, they can rely on the system to take them to the right floor right away. Fast and efficient, and no more frustration waiting for an elevator during the morning rush hour. The average waiting time has been cut by 16%. And much more ambitious is a project that's already in the works. Imagine taking an elevator into space. One of Japan's leading construction companies, Obayashi Corporation, envisions connecting bases on the ground with a space station orbiting 36,000 kilometers above the Earth. If this dream becomes reality, we could build launching points for deep space exploration. And why not spend a holiday in a space resort? So as you can see, for elevator technology, even the sky is no longer the limit. Thanks for watching, and see you next time on JTech Innovation and Evolution.